Here we'll be looking at basic concepts of electrochemistry, galvanic cells, electrode and cell potentials. This is material you certainly know from your general chemistry, but you want to refresh it in your memory.
Okay, so let's consider what happens when we put chunk of zinc metal in solution containing copper sulfate. Copper sulfate dissociates into Cu2 plus ions and sulfate ions that play no role in further consideration. When zinc is immersed in solution containing copper ions, zinc atoms are oxidized and transfer electrons to copper ions. That's what happens here. As a result, copper becomes metallic, copper, neutral, and zinc ions are coming into solution. Zinc ions are oxidized and dissolved. Copper ions are reduced and deposited on surface of metal. Overall reaction can be written in such fashion. Solid zinc reacts with Cu2 plus ions in water to make Zn2 plus ions in water and solid metallic copper. Electrons are transferred from one neighboring atom to another. Essentially, these species contact each other. Let's look at another design of the same system. Here, we take one beaker in which we put zinc salt. We can take zinc nitrate or zinc sulfate, doesn't matter. Then we put piece of zinc metal here. In another beaker, we are putting copper salt and a chunk of metallic copper. So we have exactly the same ions in solution, just separated in two separate beakers. Zinc 2 plus ions are sitting here, and Cu2 plus ions are sitting in the right beaker. We have copper metal and we have zinc metal. The chemistry is exactly the same as it was in previous example, but electrons need to travel through the wire from zinc metal to copper metal. Movement of electrons from zinc to copper creates positive charge build up on zinc and negative charge build up on copper. Electrons are traveling. Now, at this point, the reaction will stop because the copper will be positive and positive copper will repel copper ions. Zinc ions from negative will not go into solution. What we can do, we can put a bridge between them. So ions, in this case it's potassium and nitrate, ions can travel through this bridge and conduct electricity. So negative charge build up from here and positive charge build up from right side will disappear because ionic current will go through this bridge. So we have a full electrical circuit. Electrons will travel from here to there and ions will travel in this direction. Negatives here, positives there. As a result, we have a cell with some voltage between these two electrodes. If two half cells are connected by wire running from zinc to copper, electrons spontaneously flow from the zinc electrode, which is more negatively charged and therefore repels electron, to copper electrode. As electrons flow away from zinc, the N2 plus equilibrium shifts to the right according to Le Chatelier principle, and oxidation occurs. As electrons flow to copper electrode, CuC2 plus equilibrium shift to the left and reduction occurs. Flowing electrons constitute electric current. This idea was first implemented by Alessandro Volta in year 1800 exactly, but his design was based on earlier ideas of Luigi Galvani. So the cell can be named voltaic cell or galvanic cell. It's exactly the same. The first design by Volta contained copper and zinc discs that were separated by cardboard or felt spacers soaked in a salted water, which was electrolyte. When no current is coming from this packing, that's named Volta pile, like that, that's original pile. It generates around 0.76 volts with brine electrolyte from each cell. If you have 6 cells, for example, you have 456 volts of electromotive force. Back 200 years ago, people were making literally thousands of such cells for the whole battery, getting very high currents and very high voltages. Entire 19th century electrical industry was powered by Volta's battery. Lots of discoveries were made using it. Now, how we draw that schematically? We can represent chemical cells with compact notation called cell diagram or line notation. We can represent our cell as the following. Zinc solid, straight line separating from solution of zinc ion. Bridge is notated as double line. Then you have Cu2 plus ions in water and copper solid. So we write oxidation half reaction on the left and reduction on the right. Double vertical line indicates salt bridge separating two half reactions. So one half reaction here, one half reaction there. Substances in different phases are separated by a single vertical line, which represents boundary between phases. If there are several reactants or products in the same phase, we separate them with comma in line diagram. For example, I have magnesium wire and magnesium chloride here. So I'm writing MgS, solid line, and magnesium chloride solution. Bridge is connecting it to solution that contains both FeCl3 and FeCl2, so two species in solution, and the electrode is platinum metal. We are writing like this. As you can see, platinum is absent in our half reaction. In voltaic cell, potential difference between two electrodes is cell potential. The cell potential depends on the relative tendencies of reactants to oxidize or to reduce. Combining the oxidation of substance with strong tendency to undergo oxidation and reduction of substance with strong tendency to undergo reduction produces large difference in charge between two electrodes and therefore high positive cell potential. Cell potential for electrochemical cell depends on specific half reactions occurring in half cell, and measure of potential energy difference per unit charge between two electrodes. We can think of electrode in each half cell as having its individual potential, called electrode potential, so difference between cell and electrode potential. Overall cell potential is difference between two electrode potential. So we just taking two potentials, calculating its algebraic difference, so have positive or negative number. We cannot measure electrode potential of half cell directly. We can only measure overall potential that occurs when two half cells are combined in a whole cell. What we can do? We can assign the potential of 0 to some specific electrode. So we need to find particular type of half cell, measure all other potentials relative to this half cell, and say that this potential was 0. There is common agreement to use so-called standard hydrogen electrode, SHE. Why? So the reaction is fantastically simple. Two very simple ions, two H plus ions, protons, react with two electrons to make H2. This is the simplest possible ion reacting with electron and making simplest possible molecule. That's why, again, it was very convenient to assume this is exactly 0 volts. That's exactly, by definition, there is no error sign here. How we do it technically? Inert platinum electrode is immersed in 1 molar hydrogen chloride solution, and hydrogen gas at exactly 1 atmosphere pressure is bubbled through this solution. So standard pressure 1 atmosphere, standard concentration is 1 mole, and surface is platinum. Now, if we take this standard electrode and connect it to electrode of another half cell of interest, in this case zinc sulfate, we can measure potential difference or voltage between two electrodes. Since we assign standard hydrogen electrode 0 potential, we can now determine electrode potential of other half cell. Because we assigned SHE potential of 0, we calculate it in such a fashion. So potential or voltage of cell is potential of cathode minus potential of anode. Now, total voltage I can measure simply by good voltmeter. So in our case it's 0.76 volts. Now cathode by definition is 0, which means anode will have minus 0.76 volt. This potential, as you see, is negative. Now we can connect our standard hydrogen electrode to copper electrode immersed in 1 molar Cu2 plus solution. The measured cell potential is 337 volts, but the direction of current is different. A Cu2 plus electrode is at more positive voltage than standard. So we can write the diagram as following, and write again. Voltage of cell is potential of cathode minus potential of anode. In this case, our anode is hydrogen electrode because current is going from here to there. So our voltage is simply potential of our Cu2 plus electrode, and it's positive number. Now, by convention, standard electrode potentials are always written for reduction half reactions. We write standard electrode potentials for two half reactions just discussed as Cu2 plus 2 electrons Cu metal plus 0.34 volts, Zn2 plus 2 electrons to Zn minus 0.76 volts. ESL is positive for spontaneous reactions and negative for non-spontaneous reactions. So this process goes spontaneously. Standard electrode potentials for several common half reactions are listed in your textbook, both in table and in the appendix. They can be found in Wikipedia and many other sources. Let's look at some of them. So usually all of them are measured, as you remember, at 25 degrees. So this larger redox potential is, or standard electrode potential is, stronger this oxidizing agent is. So the strongest oxidizing agent in this is fluorine gas with 287, cannot exist in water. In aqueous solution, the strongest would be something like 1.7, 1.8. For example, MnO4 minus plus 8 H plus 5 electrons giving Mn2 plus 4 water molecules 1.51. PbO2 with H plus gives 169. So we are going lower. We have lower strength as oxidizing agent. Now, if we reverse reaction, it will be a reducing agent for reversed reactions. So these are very weak reducing agent and going down the strength. Now here in the middle we have 0 for our standard electrode potential, 2H plus 2 electrons making H2 gas, exactly 0. Below we have very weak oxidizing agents and very strong reducing agents. Question. Potential for reaction K plus 1 electron making K solid is very small number, minus 2.94 volts. This means K plus is very poor oxidizing agent, doesn't readily accept electrons. Does it imply that K plus is strong reducing agent? Answer is no. To be strong reducing agent, K plus would make K2 plus, which is absolutely impossible. Who is this strong reducing agent? That's K. So when we're talking about reduction, we are looking at opposite direction. Reducing agent oxidizes, so reaction is going from K to K plus, from right to left. How to predict spontaneous direction for redox reaction? Half reaction with more positive potential attracts electrons more strongly and will undergo reduction. So reaction with more positive will go as it is written in table. Half reaction with more negative potential repels electrons strongly and will undergo oxidation. This reaction will go opposite direction to the equation listed in the table. Any reaction in table is spontaneous when it's paired with reverse of any reaction listed below it on the table. So let's look at example. Cl2 plus 2 electrons, 2 Cl minus. Very similar reaction. Br2, 2 electrons, 2 Br minus. Redox potentials are 136 and 109. This is above this. So above you have Cl2, below bromine. Now 136 is larger than 109. So the first reaction will go direct. This reaction will go opposite. You need to change the direction. So spontaneous reaction would be Cl2 plus 2 bromide ions, it's minus here, 2 bromine, Br2, and 2 Cl minus, Cl2 plus 2 bromide, Br2 plus 2 chloride. This is spontaneous direction. Next, let's predict whether metal will dissolve in strong acid. Strong acid, you remember, this compound that makes H plus ions in water. So the reaction will be H plus to H2. Now this reaction H plus to H2 have electric potential of 0. So metals whose reduction half reactions are listed below reduction of H plus to H2 will dissolve in strong acids. Metal listed above it do not. Now, who are listed below? Metals with negative standard potential, below 0. We can say exactly the same statement. Metals with negative standard potential will dissolve in acids, and metals with positive will not. Important exception is nitric acid that can oxidize metals through reduction of nitrate ions. So NO3 minus reacts with H plus and 3 electrons to make NO. This redox potential is much larger than 0.96. Let's look at examples. There are plenty of metals like iron, zinc, potassium, sodium, so on, with negative potentials. That's clear answer. Now let's look. Cu2 plus 2 electrons make Cu, positive number. Will not dissolve in strong acid. Ag plus E minus Ag, 0.80 will not dissolve in strong acid, but these two numbers are smaller than 0.96. So these two metals, copper and silver, will dissolve in nitric acid. Let's look at gold. Au3 plus to gold metal has very large potential of 150. Gold does not dissolve in strong acid, and 150 is larger than 0.96, so it will not dissolve in nitric acid as well.